This is Lab 5 Kinetics by Luisa Castro. What is chemical kinetics? Chemical kinetics is a branch of a physical chemistry that focuses on the rates of a chemical reaction. By definition, kinetics means the study of motion. It also describes the formation of bonds and deformation of products through the intermediate of transition state. What are we trying to accomplish in this lab? In this experiment called chemical kinetics, we will be measuring the rate of an S1E1 reaction and demonstrate first-order kinetics, as well as determine the rate constant K from data collected, because we want to determine the rate at which T-butyl chloride disappears. Here, T-butyl chloride interacts with H2O and IPA to form T-butanol, isobutene, and HCl. What is the procedure? First, we will add a 10 milliliter sample of the reaction using a 10 milliliter volumetric pipette to an Erlenmeyer flask that contains a 10 milliliter of isopropanol and record the time. We then titrate the quench sample or aliquots to the end point by using a burette that's filled with 0.4 m sodium hydroxide 5 different times. Here we want to measure the rate at which T-butyl chloride disappears, our substrate, which in terms is equal to the rate of formation that HCl appears, product. A final aliquot is performed after the reaction is complete to determine the value of H+, hence why we record the time. Quenching, a process known to decrease the intensity of a given substance, is performed because the IPA is less polar than the IPA and the water mixture. Here, the IPA and H2O is our reactant. We then titrate the quench sample, or aliquots, to the end point by using a burette that is filled with 0.4 m sodium hydroxide 5 different times. We repeat this process until the reaction is complete. A change in a purple color indicates that NOH was titrated. We collect the 5 different times as the point, as well as the infinity point. Diving deep into the mechanism. Here we see the formation of T-butanol, isobutylene, and HCl from T-butyl chloride, where H2O and IPA is our reactant. In order to understand this mechanism, we must understand SN1 and E1 reactions. SN1 reactions. It's a nucleophile substitution in which the rate-determining steps involves one component. SN1 reactions are unimolecular that proceeds through an intermediate carbocation. A positive charge on a carbon is called a carbocation. This equation is often shown as having first-order dependence on electrophile and zero-order dependence on nucleophile. Only one molecule splits apart. The first step is the rate-determining step, where the leaving group is lost and the carbocation intermediate happens. This all well occurs within one step. Since the rate is controlled by the loss of the leaving group, the weight of the reaction is highly dependent only on the concentration of the substrate and not the concentration of the nucleophile. The carbocation are technically all in the same plane. Thus, the nucleophile can attack either side, resulting in both enantiomers formed. This leads to a racemic mixture of the enantiomers. The stability on a single substrate for its rate reaction. The stability of carbocation is highly important to the SN1 reaction, since it is a unicellular reaction that depends on a single substrate for its rate of reaction. In our experiment, T-butanol becomes a product of SN1 reaction since only one molecule splits apart and the leaving group Cl no longer becomes part of the compound. H2 and IPA are good reactants because they attack the Cl in the tert-butyl chloride and creates the products of HCl. The HCl is formed through the splitting of this attack. The C then undergoes carbocation through its rate-determining step and splits the Cl. E1. Like SN1, E1 is a unimolecular elimination reaction where the removal of an HX substituent results in the formation of a double bond. A two-step reaction occurs, 1. Ionization and 2. Deportation of the carbocation. The carbocation results in the formation of an alkene product from the deprotonation of a hydrogen nearby. The carbocation is formed due to the leaving group leaving on its own, since it takes the electrons in the bond with it, thus impacting the carbon that was attached to it by losing its electrons. The double bond is then formed once it becomes a carbocation and deprotonates the intermediate carbocation, thus donating its electrons to the neighboring C bond. The more stable the carbocation is, the faster the formation of E1 reaction will be. Isobutane is a product of an E1 mechanism. We can clearly see that there is a double bond form, as well as the HCl. What is titration? Titration, a method of quantitative analysis to determine the concentration of a dissolved substance by a gradual addition to the sample of a known quantity or of another substance in hopes of determining the concentration of an identified analyte. Why are NaOH and HCl in our experiment? In our experiment, we are adding NaOH, our titrant, to the solution. It is important for NaOH to be added slowly, or else the results will be inaccurate. If too much NaOH is added without a slow pace, you will overshoot the appearance of HCl and the disappearance of T-blue chloride. The bright purple color should be very slight, and it is important to rotate the Erlenmeyer flask after droplets of NaOH have been added in order for the whole substance to be able to react with the droplets. The bright purple color change, where one can no longer add NaOH without the presence of color, will indicate that HCl is at the equivalent point. The solution is acidic due to the excess presence of HCl in the flask. However, there will be an excess of NaOH, which will turn the solution basic after this equivalent point, indicating an acid-base change. These are our lab results. As you can see, there is a linear increase from time in minutes to total volume of NaOH and ml. Affinity is reached at around 12.1 milliliters of NaOH after minute 100. What are the possible errors? Errors in titration include overshooting NaOH onto the Erlenmeyer flask and causing the appearance of HCl way too soon. This will give you a wrong volume of the point of titration. Not reading the flask correctly can also cause a mistake in units. Spilling of such substance can occur if one is not carefully moving substance from one flask to another. It is highly recommended to use a pipette for this transferring of liquids. What is the conclusion? All the data that I was looking for, I found. If the data was not correct, then the point of affinity would be at an earlier or later minute than it was, as well as the amount of ml of NaOH it took to perform this titration. Next time, I would be more careful about the amount of droplets of NaOH I am releasing onto the Erlenmeyer flask. Thank you for everything.